Hello everyone, and welcome to the second part of our course. Today let me start with a little bit of common sense reasoning. You know, it is absurd to try to drive screws with a hammer or to use a magnifying glass to try to pick at atoms or molecules, or to try to unclog the pipes with a toothbrush. We humans have been perfecting the art of creating a perfect instrument for every task. There are dozens of types of knives, for example. One is for butter, one for cheese, a different one yet for fish and steaks. Some knives are used in fights, and some knives are good for tanning. But no knife is good in driving down nails, cracking nuts, or shaping marble into sculptures. For that there are other instruments. So using an appropriate specialized tool makes you radically more effective in your task. However, when we are building computer systems, we keep trying to solve all kinds of problems using variants of the same tools. Languages like Python, Java, C are all describing computations sequentially in an imperative style. It makes them conceptually close one to another. And so they are also sharing lots of strengths and weaknesses. These tools are popular because they are able to do anything, but they are not exceptionally good for anything. In reality, there are ways of organizing computations that are radically different from C or Java. They may be exceptionally good to solve particular kind of problems, but terrible to solve other problems. If you master some of such specialized tools, you will be radically more productive and capable of providing quality solutions for extremely complex problems, just because you are using a screwdriver to drive screws, while everyone else has a butter knife. So here is my promise to you for today. At the end of this part, you will have been exposed to new ways of organizing computations and to practical examples of their benefits. This will enable you to craft very complex programs and systems easily and with less bugs. Additionally, once you learn the basics of assembly in the next part, the first assignment will be much easier for you if you are going to use the wisdom learned today. So today we will talk about models of computation and interpreters in the sense of a functional component of computer systems. As usual, we are going to start by providing some references and useful links. If you want to learn more about what we are going to talk today, then certainly I would advise you to take a look at those references and links. Check them out. In the previous part, we have learned what systems and computer systems are. We've learned that the source code is not a system because it is not active. But a running program is a part of a hybrid system incorporating hardware and software parts. We've learned that the systems can be decomposed on parts structurally or functionally. We've learned that complexity is the ultimate challenge for developers, and computer systems are very complex. However, there are powerful approaches that help us reducing the complexity of systems, namely modularity and abstraction. Modularity is about designing smaller modules, crafting each module in isolation, and then composing the system out of those modules. And abstraction is about forgetting the inner structure of modules and describing their behavior instead. Computer systems are very complex and they are also very diverse. And in order to somehow categorize them, we propose to decompose them functionally and study their components. And there are three common types of functional components in computer systems. Interpreters, which are active components of the systems, they execute actions or react on events. Memory that stores data, and communication link that connects parts of systems. In this part, we will focus on interpreters, one of three types of functional components in computer systems. Interpreters are active elements performing actions that constitute computations, either proactively or as a reaction to some events. Various interpreters may use radically different ways of describing computations. So what is it exactly that an interpreter is doing? We have provided some examples of interpreters in the previous part, such as word processors or games or browsers or compilers. Some interpreters are programs that accept a source code written in, say, Python and execute it. But from a systems perspective, these are just a particular case of interpreters as functional components of systems. And today, we are interested in precisely such interpreters that are executing in programs. When we program, we put on paper our ideas about computations. And we need a fitting language to express these algorithmic ideas. How do we describe an algorithm? And before we try to answer these questions, imagine we are telling someone how to perform some trivial action. Try to explain some real-world action like that we are performing often enough, like going shopping from home to buy some bread or rice. And everyone will answer based on some evident basic actions, such as open the door or take the key or leave the house, or move the right leg forward 20 centimeters, or let's say contract the following set of muscles in your leg. Or someone may tell you, well, here is the starting point, it's your home. Here is the end point, the shop. And you have to walk the shortest path. And there's a road here, you see, and crossing the road is only allowed in this spot. And then figure out how to construct a path from start point to the end point that will satisfy those constraints. And so we see that giving a definite and precise answer to the question how to get from your house to a shop is not really trivial. And in answering this question, there are two problems. The first one, the answer to this question is an algorithm. And we need a fitting language to express an algorithm precisely and unambiguously. Natural languages, such as English, are imprecise and ambiguous, so they are not really a good fit for that. Then, the second problem is that in our description, we use a set of operations, but we never fix a basic set of operations. For each operation, we may ask ourselves, what is that? How precisely do you do that? What is it, moving your leg or taking the key? Or how do you even tell what object is the key and what object is not a key. What do we have to grab exactly? So we require a sort of basis, a foundation, a set of basic actions and ways of combining them. There are, of course, infinitely many ways to describe algorithms, and there are also infinitely many ways of laying foundations for those descriptions. And such foundations are called models of computations. A model of computation is just a set of basic operations, and we use these operations to express algorithms. Some of these operations may combine other operations. For example, pick two other operations and execute them sequentially, one after another. Or pick two operations and execute them in parallel. Naturally, we can create all kinds of models of computations, and only our fantasy is our limit. But what for? What's the catch in creating lots and lots of models of computation? Well, let's think about real life and how do we think about problems in real life. In real life, some of the problem solving is procedural in nature. For example, cooking a meal is a sequence of steps that leads to the result, a cooked dish. But we are not always solving problems procedurally. Imagine you and your friends want to go out and eat something, but you have different preferences, different tastes. And you have a problem, and you are trying to find a solution for it. You and every one of your friends, you have a certain set of constraints. One of you doesn't like chicken, others do not like vegetables, for example. And what's going to be your approach to solving this problem? It's not going to be procedural. You're going to lay down a set of constraints and then try to find a solution that satisfies all constraints imposed by your friends. The same constraint-based approach works when you are scheduling. When are you going to complete your assignments? You have constraints such as deadlines, events that happen on fixed dates, classes every day, etc. And the solution to this kind of problem is a schedule where all your tasks have time slot allocated for them, and all constraints are satisfied without collisions. Another approach, let's say when a writer is working on a book, and the book passes through a certain pipeline. Every chapter starts like a draft made by the author, and then it passes through several editors. Each editor has a role and applies a certain process to the book. And then the draft goes back to author, and sometimes the cycle repeats. Such pipeline-based approach is typical for a lot of collaborative tasks. And so we've given 3 examples of approaches: procedural, constraint-based, and pipeline. And of course, there are many, many more. But they show that each problem benefits from picking an appropriate tool to solve it. For computational problems, choosing an appropriate model of computation makes solving it easier, faster, and the solutions have less bugs. But using the same model of computations may work terribly or not work at all for a different problem. Traditionally, students start programming imperatively with languages like Java, Python, or C. These languages, and also Scala, Ruby, C#, Kotlin, Go, JavaScript, lots of others, They all have similar models of computation. It can be described as an abstract machine with von Neumann architecture. It has a linear flat memory, readable and writable, and the program is sequential. In such programs, every statement is a command. Do this or do that, compute this variable, output it, call a function with this and that argument. Hence the name for this programming style, imperative programming. It is indeed possible to express any algorithm in the von Neumann model of computation. But it is, of course, not necessarily the best option for all problems. A good strategy is providing a solution in an appropriate model of computation, for example, constraint-based. Because the appropriate model of computation makes it expressing the solution straightforward, producing a solution on this level is easier. The second step is encoding the solution in the target language, whatever you are using, C, Java, doesn't matter. Then we can just code the solution in the target language, and the translation between two languages, the language with like an appropriate model of computation and the target language, can be automated through either code generation tools like transpilers, translators, or whatever, or through domain-specific languages implemented directly in the target language. Alright, let's pass to the first model of computation that we are going to study in this course. And this is not very orthodox model of computation. It's called finite state machines. A finite state machine is an imaginary computer, an abstract machine. It has a fixed set of states, and in every moment of its functioning, a finite state machine is in one of these states. Finite state machines are observing the external world and reacting to the events. And the reaction depends on the exact state they are in. So once an event occurs, the machine checks the rules of transitions associated with the current state. Each rule is in form: if the machine is in state A and the input event is I, then jump to the state B and issue a reaction O. Then the input event is consumed, so it will not affect the functioning of machine anymore. States A and B may not necessarily differ, so the rule may create a loop. And it is not mandatory to show any reaction to an event either. Events may or may not result in a transition from current state to a new state, because we can just return to the same state. The computations start in a distinguished initial state. The computations are considered complete if all input events happened and we ended up in one of the distinguished final states. And the outcome of the execution can then be encoded by which exactly final state did we arrive into, which final state was the last. On the diagrams, we denote states with circles. Like here you see states A and B, and they are being connected with a rule. If the input event is I, then pass through from A to B and output the reaction O. So we annotate arrows with both events to which machine reacts by following this transition, and the explicit reaction O, if there is any reaction, of course. The initial state has an arrow into it annotated with the word start. The final states are outlined in double circles. So the first finite state machine that we are going to study has two states, A and B. A is the initial state and it is also a final state. This machine observes some global stream of zeros and ones, and an event is consuming one digit from it. The machine is arriving in the final state if the consumed string contains an even number of ones. So 0 ones, or 2 ones, or 4, 6, etc. Now suppose that the input stream contains symbols 0, 0, 1, 1. So there will be 4 events. Let's trace the execution of this machine to understand what is really going on. So the initial state is A. We start from here. Then we observe a 0. So we are taking this transition and we return to the state A. Nothing has changed, and for a good reason, because no matter how many zeros we have, we don't have to change the counter of ones. The second symbol is 0, and again we are taking the same transition and we are always in the state A. Then the third event, the third input symbol is 1. For that we have to jump into the state B. In the state B, if we get 0, we also stay in state B, we don't move. But the fourth event is 1. So on the string 0, 0, 1, 1, we are going to get back to the state A, and this is where we are going to end up. We are going to stay in the state A after these 4 events. And as you see, every time we consume 1 from the input stream, we change the answer from yes to no and vice versa. In this context, we are in the state A if we have read an even number of ones so far from the input stream, and we are in the state B otherwise. But actually this machine only knows how to answer yes for strings containing an even number of ones, but it doesn't really know how to say no, because we only have one terminal state, one final state. Okay, let's proceed to the next example, shall we? Next example is a silent number, and this is something a bit more complicated. Here we want to answer yes if the input string is a number, possibly with a sign. A number contains at least one digit, and it also may start with a sign, either plus or minus. Now, what would be examples of valid numbers? Let's think. 10 is obviously a valid number. Plus 32 is also a valid number. Minus 999, also a valid number. We also want to say that plus 0 or plus 0.2 are valid numbers, even if they look a bit bizarre. But what kind of numbers would be invalid? Well, let's say minus 1 is not a valid number. Or plus is not a valid number. 38 minus, also not a valid number. All right, we start in the state A. Let's see what exactly is going on here. The first character can be a digit or a sign. So a digit or a sign, plus or minus. If it is a digit, then we get to the state C. And bingo, this is already a success. Every next digit that we are going to read will let us stay in this state. And this is correct, because once we get a correct number like +9, we can add any amount of other digits to it and it will stay a correct number. Alright, but what's going to happen if we, let's say, read a sign? If it was a sign, then we pass to the state B, which means that we have read the sign and now we only expect digits. Then we proceed by reading at least one digit here. And in this case, we are going to proceed by reading one or more digits, like in the previous clause. Once we run out of events, if we are still in C, then the answer is yes. The input string is actually a textual representation of a signed integer. But note that this does not really parse the number yet. It does not produce the actual number whose digits we have processed. But we are halfway to solving this problem too. In mathematical language, events are called input symbols and reactions are called output symbols. But we deliberately have not forced the mathematical terminology in our explanations, because in the real world, when we are implementing finite state machines, usually input events are just input symbols are just like global events, and output symbols are really the reactions issued by the system. Indeed, neither input or output symbols have to be characters from some string. But what are like the typical areas where state machines are useful? It's very often used in robotics. In this case, events are going to be sensory data and user actions like pressing button or interacting with something exterior to the robot. And reactions are going to be robot actions like turning right or grabbing something with a mechanical hand, or pouring coffee if this is a coffee machine. Second large area is network protocols, where incoming packets are going to be events and reactions are going to be outgoing packets. Another area that comes to mind is implementing artificial intelligence in a cheap way in computer games. In this case, we can think about states in two contexts. The first context, let's say, is the character progression in quests. So as you progress through quests, the state of the quest is going to be different, and your interaction with certain NPCs is going to be different. The second thing is, the second context is the state of the non-player character itself. It can be applied to, for example, the character jumping or walking or crouching or swimming or being active or inactive. Or it can be also applied like in RPGs when you have a semblance of life, when a character is living in town and it has to do a certain routine. Walk around, cook food, do the shopping, etc., etc. So this kind of algorithms are easily being encoded as finite state machines and then being implemented in a very efficient way. Now let's take a look at some more examples in more details. And we will start with TCP protocol. Every day we are using TCP protocol to exchange data through internet. State machines describe pretty well how a program interacts with another program following the protocol. Both parties participating in the exchange have internal state that maps exactly to one of the states on the diagram below on the slide. This machine reacts to the following types of events. First kind of event is we have received a packet of specific type. And on this diagram there are at least three types of packets, I think, more like four. SYN, ACK, RST, and FIN. Another kind of event is an application has performed something, some action. For example, closing connection. And the third type of event is some kind of global events from the outside world, like connection timeout, for example. And every time there is some event happening in the current state, we can issue some sort of reaction to it. What's interesting to note is that all those events are global relatively to the machine. No matter which state are we in, these events are observable. And this is an important point that is characteristic to the situations where finite state machines really shine, and when using them is appropriate. The next example are, of course, regular expressions. And regular expressions allow us to describe a pattern that you can search in a text for. It's like searching for a substring, but the substring shouldn't be matched exactly, but there is some freedom to that. So how does it look like? We'll check out some patterns that we can see on the slide. For example, if there are just symbols in the regular expression, the symbols are usually being matched against themselves. So a string hello is going to get matched against a substring hello. But there are also some symbols with specific semantics. For example, if you put a dot in a regular expression, a dot will match against any letter. And if you put a symbol and then a character plus, it will mean one or more matches of the symbol that was before plus. Like here, for example, hello underscore dot plus will match with any string that starts as hello underscore and then has one or more letters. And those letters can be different. They don't necessarily have to repeat. Now the typical constructions in regular expressions are range of characters. For example, in the second case, it's from 0 to 9, and then you have plus to describe that there are at least one of digits. So one or more symbols in class from 0 to 9. It's not really important to dive into details. How do regular expressions look like, and what are the options to use them? The possibilities are really infinitely many. But I think that your favorite text editor probably knows how to use it, knows how to handle regular expressions. So whenever you are going to the menu and choosing the option of search and replace, you probably are able to not only put the exact string that you want to replace, but a regular expression, and then replace everything in text that matches this regular expression to some sort of different string. But the interesting thing about regular expressions is that they are usually being implemented through a construction of a finite state machine based on them. We've seen already today how a finite state machine can be used to parse a certain string. And basically, regular expressions are equivalent to finite state machines in this regard. Everything that we can parse using finite state machines, we can write a regular expression for that and match against such strings. For the next example, we are going to talk about the process states. A process is a container for the resources of a running program. In this section, for the sake of simplicity, we will assume that each process has only one thread, one execution thread. In a classic 5-state model, each process is being born, initialized, and then its thread is scheduled for execution. Once initialized, the process becomes ready for scheduling. A scheduler dispatches it, giving it time to be executed by CPU. Here we are in the state ready. Once the process has been created, it becomes ready for scheduling. Then a scheduler dispatches it. And it means that once we are here in the state running, we are really using the resources of CPU. And while we are running, three things may happen to us. First, CPU is not going to run only one process indefinitely. The process may deplete its time, its quant of time. Then it gets interrupted by the timer and becomes ready for dispatch again. We're getting to this state again, the state ready. The second option is that the process can initiate an input or output action, like reading from HDD, from hard disk drive. And such operations are really slow. It doesn't really make sense to keep the process executing on the CPU while it is waiting for an I/O operation to complete. So in this case, the process gets into the state waiting, and it's not being executed on CPU anymore until the I/O operation is completed. Then the process returns to the ready state and can be scheduled again. The third option from the state of running process is that the process exits. Then it becomes terminated, and eventually the associated resources are released. And notice again that all these conditions are global compared to, related to the process itself. Of course, in many real systems, this model is but a useful approximation, and the full model will contain more states and more transitions. And of course, if you create your own operating system or a language virtual machine like Erlang virtual machine, or any kind of other execution platform, your concept of processes may be different. Nevertheless, chances are that using state machines to describe the evolution of your process is going to be beneficial to you. Alright, now let's further explore the finite state machines by pinpointing the key differences from the typical von Neumann machines that we are so used to. When people study finite state machines, they often have a desire to bring in some properties familiar to them from other programming paradigms. So here are some key differences. First, the state of computer for an assembly language programmer is fully characterized by values of its registers and memory. The state of the finite state machine, however, is opaque. We only know about the current state, that it's like this circle or that circle. It's one of a fixed set and we don't know what's inside. Second, in the finite state machines there is no memory whatsoever. No variables, no registers, no stack, also no assignments, no if then else constructions, no loops like while or for, nothing like that. So it is a completely different abstract machine. It's not a von Neumann machine in any regard. There's nothing but states and transitions between them. However, from a practical perspective, when we program and we program finite state machines, so to say, we can still use memory, but the memory should be placed outside the finite state machine. If we place memory cells outside and treat writing to them as output actions regulated by transitions, then we stay within the capabilities of finite state machines. And it is important to stay within them for a number of reasons. We are going to talk about limitations and the power brought from limitations a bit later. Coming back to parsing a string of characters with finite state machine, we can consider the string external to the finite state machine itself, global in a way. Then we assume that there is a component which feeds characters of the string to the finite state machine and updates the current position in it. By using this trick, we completely abstract working with memory with the layer of global events to which the finite state machine is reacting. Okay, so now we want to talk about some notions related to the behavior of finite state machines. Finite state machines are good to demonstrate notions of determinism, not determinism, undefined behavior, and totality. And these notions are useful not only for finite state machines, but also for more conventional programming languages. Let's see what this is really about. And we start with non-determinism. We know that once a finite state machine observes an event from its current state, it picks a transition annotated with the right event and jumps to another state. But from the way we were constructing finite state machines, it is possible to have several transitions annotated with the same events. And so what will happen if the following finite state machine we observe an event 3 while being in state A? You see there are two errors with this event. There are several possible transitions. In order to find a reasonable course of action, we have to define more precisely what is the result of the functioning of a finite state machine. And for a given input stream of events, we will call a behavior of finite state machine a sequence of transitions from the initial state to a final state. So a behavior is a trace of execution. Now, what if there are multiple outgoing errors annotated with the same event, and we don't know what to choose? Instead of having a single behavior, we will assign to a finite state machine a set of behaviors, all of which are equally valid. And this is where what we call non-determinism, an ability to have multiple behaviors. And non-determinism does not mean that the single behavior is going to be chosen at random. It is just what it is. One system has many behaviors. However, when we implement the finite state machine as a program in a deterministic language, we can't do that. So we'll have to choose what to do. And the options here are, we can either keep track of all behaviors and show them to user somehow, or we can select any single behavior from the set of possible behaviors and just say that, okay, here is the behavior. And the concept of behavior is not specific to the finite state machine, of course. It also applies to C, Java, and any other programming language. The program execution can be viewed as a sequence of transitions between the states of the abstract machine of the language. Then the most fine-grained definition of behavior would be a sequence of transitions between the states of abstract machine for a given input. Let us demonstrate how a program in C can have multiple behaviors, and be non-deterministic, just like a finite state machine. Consider two functions, f and g. Each of them outputs its name and returns an integer 1. And so what is going to be the outcome of evaluating an expression call to f plus call to g? We are unable to evaluate this expression in one step, so we will split it into sub-steps. Two for evaluating the functions f and g respectively, and one more for adding their results. However, in C, the order of evaluating left and right operands of plus operator is undefined. It means that for the expression f plus g, we can either evaluate f first, then g, or g first, then f. The resultant value will be the same because addition is commutative. But be careful, these functions are also printing their names on the screen. So depending on which function will be evaluated first, the user may see on screen either fg or gf. These two options correspond to two traces, which we are seeing here. So in the first trace, we start by evaluating f. Here it is. Then we have to evaluate g. And in every state, as you see, we are gradually showing how the expression gets evaluated. And then from this state, of course, we get into the state where we have evaluated everything. Now, the second option is if we start by evaluating g. Then we go like this and like this. So basically, the problem is that there are two ways of getting to the state 1 plus 1 from the state f plus g. And depending on which route did we take, the outcome is going to be different. And so these traces, they form a set of behaviors, not a single behavior, and the C program actually has multiple behaviors. However, when it passes through compiler, the compiler selects one behavior out of this set, and the compiled program, the assembly program, will have this single behavior. But note that compiler is not obliged to select this or that behavior. Once you change the source code or choose a different set of compile flags and then recompile your program, the compiler might select a different behavior. And this different selection may lead to a smaller compiled binary size or to a faster program, or the selection may be completely random. Having multiple possible behaviors may be dangerous. Imagine that one of the actions is reading a line from some file and another action is writing a line to the same file. And these operations may happen in any order. Worse even, if the order is as you expected, you may miss the possible bug altogether until it happens in one of the future versions of your program. So the C program is allowed to have many behaviors and the compiled binary has only one behavior. This is what we call a compile time non-determinism, because the compiled program is deterministic, and in compile time the compiler kind of resolves their non-determinism. There may be cases of runtime non-determinism, where each time the program is being executed, it may have a different behavior. This may be a result of concurrent execution with an incorrect synchronization, data races, etc. So, incorrect multi-threading applications, for example. Alright, we have seen an example of non-determinism when the behaviors are many. But can there be no behavior at all? Let us take a look at this finite state machine again. And so we are in the state A, and the input event is 1. What do we do? There is absolutely no transition for this type of rules. We have really nowhere to go. In this case, we postulate that this trace has led to undefined behavior. We literally do not know how to define this behavior. In languages like C, undefined behavior is also present for several reasons. Take, for example, null pointer dereference. When we dereference a pointer, which is a null pointer, the result of this is undefined. It can be anything. Imagine that we assign a specific semantics to dereferencing null pointer. And then the program will have to check all pointers before dereferencing them. If there is a possibility for a pointer to be null, then the program will have to check it, and if this is the case, demonstrate some specific behavior. Potentially, this may degrade the program's performance because of all those additional checks. Instead of this, the language relies on the programmer's skill. It demands the programmer to promise that they will never dereference a null pointer. And only then will the language guarantee a well-defined behavior to the program. Okay, let's go back to the same reasoning. So a C program can have multiple behaviors, can have single behavior, and can have no behavior. But a compiled assembly program is always doing something well-defined. Whenever an undefined behavior happens in C program, in assembly program, anything can happen. Nothing, or an immediate runtime error, or an error later someone during the execution, a silently incorrect computation result, etc. This is how undefined behavior can produce problems for you. Alright, can we protect ourselves against undefined behaviors? Some finite state machines do not exhibit undefined behavior no matter which events they observe. This obviously happens if for every state there is a transition for every possible event, a rule on where to go. For example, consider this state machine. Some finite state machines do not exhibit undefined behavior no matter which events they observe. This happens if for every state there is a transition for every possible event. For example, consider this state machine that we have already studied. And imagine that we have an input of two events, plus sign and another plus sign. And in this case, we just don't have an appropriate transition from the state B that would correspond to the second plus and lead us somewhere. How do we do in this case? We can modify this finite state machine and make it total. So a total machine will not have undefined behavior ever. And it's trivial to do. We just add an additional state that we can call, for simplicity, error state. And every time there is a transition that is missing, we want to get into this state. For each state and for each missing transition, we add a new transition to this new error state. In order to keep our diagrams compact, we will group these transitions into a single arrow and mark them as else transitions, like this. Okay, so we have learned something about finite state machines. But we haven't told one crucial fact about them. Not all programs can be encoded as finite state machines. Well, to give you a couple of examples, given an arbitrary long string, a finite state machine is unable to count its length. Each result of counting, like 1 character, 2 characters, 10 characters, each result would be a state. And if in a finite state machine, by definition, there is a finite amount of states. Finite number of states is not enough to count when the string length is unbound. Moreover, finite state machines are unable to analyze complex recursively constructed texts, such as XML, HTML pages, source code of most programming languages, etc. Indeed, think about HTML pages. You may have an arbitrarily large number of div blocks containing an arbitrarily large amount of inner div blocks, like this. And then they end. So this is one block, this is inner block, but the structure of these blocks is being described in a exactly same way. The rules of constructing a valid div block are absolutely the same, no matter at which depth it is. So, working with HTML, for example, through finite state machines doesn't usually work. We say that finite state machines are not Turing complete because they are strictly less expressive than a typical language like C, Java, or assembly. which can be used to solve a wider range of problems. But surprisingly, this limitation is not a bad thing, but a source of immense power. It is counterintuitive, but it is something that can become your secret weapon. First, once we limit the expressive power and the number of actions available, it may be easier to combine those actions. Build infinite state machines, as you see, is quite straightforward and very illustrative as long as the problem is right for that. So you can look at the finite state machine and you may immediately think about problems. Okay, we are in this state, but we don't have a transition from this state for this type of event. What should we do? Is it an error? Is it a bug? And you can even show a finite state machine diagram to someone who is very not keen on programming, to your colleagues who are not programming but who are doing some other part of projects, and you can illustrate the functioning of the system using a finite state machine. This is a very precious quality, by the way. So the first thing, limits on expressive power are making programming easier. And the second, even more important thing, it comes from theory of computability. We know that it is impossible to precisely statically analyze the execution of any Turing-complete program. For example, it is impossible to build an analyzer capable of precisely catching the null pointer dereference ahead of execution time. It's not a limitation of analyzer. It is a fundamental theoretical constraint described by Rice theorem. The inability to analyze programs follows directly from the expressive power of the language. So, if the language is Turing complete, you can not build an analyzer which will analyze and give you precise result for virtually any property of the programs. However, if the expressive power is limited and the model of computation stops supporting all algorithms, the programs may become completely analyzable. One of the verification techniques called model checking is relying on this. And we are going to give a quick overview of what model checking is and provide some examples, so that if the need arises, you would be able to dive deeper in that on your own. So what is model checking? Model checking is verifying properties of models using automated analyzers. It is a stronger tool than testing programs because it produces universal results. In other words, it's capable of proving properties of the whole program on all possible inputs, no matter how it's going to get executed. Not just some specific particular cases, like testing. And there are two ways we can approach the system design problem to employ model checking techniques. The easier way is to conceive the system as a state machine right from the start and verify its properties and then implement it. We can sometimes even generate the code on, let's say, C or other language from the description of the model. A harder way is to take an existing program and model it as a transition system. What is a transition system, though? A transition system is a looser, more generalized version of the state machines. There is no limits to a number of states in transition system, and the transitions do not need to be guided by external events neither. Each state will be an image of memory state of the program with values of all variables. Consider this simple program, for example, where the variable x has values from 0 to 3, so 0, 1, 2, 3. Because the loop body is empty, there will only be 4 reachable states in this program. A state for x equals 0, equals 1, equals 2, and equals 3. Now a slightly more complex example. Here's a program with 2 variables, x and b. B may only be either true or false, and x varies in range from 0 to 255. So the overall number of all possible states in this program, memory states, is going to be 256 times 2, so 512. But not all of these states are going to be ever happening during the execution. Not all of them are reachable. We can draw all these states on a diagram and mark them with the exact values of variables. The initial state is the one where b is equal to true and x is equal to 0. On the diagram, green states are reachable and the red states will never be reached during the execution. As you see, once we get to the state where b is true and x equals 2, we will never go to any other state. We will just stay in a loop and never leave this state. So no other state is going to be reachable. Okay, now imagine that we've managed to describe a system as a finite transition system and label each state with some properties, like the values of variables. And then our program, it all of a sudden becomes fully analyzable. The Rice theorem doesn't hold any power over us anymore. The properties are described using logical formulae. In classical logic, we can construct propositions describing the program state like x is greater than 0. And we are also able to connect them using operations like and, or, not. However, the classical logic doesn't have modality of time. For example, we are unable to express that the variable x is not yet greater than 0, but it will certainly become greater than 0 somewhere in the future. A more fitting variant of logic is called linear temporal logic. It adds several quantifiers over propositions. Like, a proposition always stays true. G quantifier. The proposition will at some point be true. The F quantifier. The proposition x is true at least until another proposition y becomes true. But when y becomes true, x may still be true and continue being true. Because we think of a program as a transition system, LTL formulae are actually applied to the traces of transitions. This way, a proposition of type, let's say, x is greater than 0 in future is interpreted as, in the future, we will certainly arrive to a state where x is greater than 0. Other quantifiers like g and u are also interpreted in terms of traces. Now, when we ask the module checker to verify a formula, it uses tricky algorithms and data structures to be able to check the properties for all reachable states relatively fast. If the property doesn't hold, then there exists a counterexample, a trace with a state where the property gets violated. In this case, the model checker will provide you this trace with every detail. One of the typical applications of model checking is verifying distributed algorithms. There is non-determinism in them, a runtime non-determinism, because several processes are acting concurrently on the same data, and the order in which these processes will issue reads and writes is unknown. It can be completely random. For the sake of example, imagine two processes working on the same array of data. The first one may perform 3 actions, and the second one 5 actions more, the first one 202 actions more, etc., etc. You see, the processes have a lot of freedom in how they are taking turns and how long are they working with data. And model checking allows us to verify properties like the first process has written a value to the variable x before the second one reads it. And if such property is violated, the checker issues a precise trace showing which process has done what. How did they take turns, which actions did they do, and how did that lead to a bug, to a violation of property. In the real world, the probability of such situation may be 1 in 1,000 executions, so trying to catch it through brute testing is totally not effective. Alright, now let's take a look at one of the existing model checkers. For this introduction, we have chosen a model checker that's called NewSMV. NewSMV is one of many modern model checkers. Like most of them, it implements its own language to describe a model. At the first glance, this language seems imperative because it has variables. However, the program is actually a transition system, and the variables are encoded into states in the same way we have shown earlier. And every state is a set of values of all variables. For example, in this fragment of description, you see 2 variables. One is x, the other is y. X varies from 1 to 100, y varies from 5 to 7. So the system with only these 2 variables will have 300 states, because one variable has 100 possible states and another variable has 3 possible states. The first example of description is going to be a simple module, one variable which can take 2 possible values. In USMV model is divided into modules, and each module is a file. It contains sections such as var or assign. Variables are defined in the section var. We define a single variable location whose value may be either L1 or L2. There are no other variables, so this system may be in one of 2 states. The section assign defines actions that happen when the system performs a step of execution. The Init Clause defines the initial values for the variables. Let me mark it on the slide. So this is where we get the initial values of the variables. Variable location is set into L1. Then the next clause describes how the variables are changed at every step of execution. In order to encode multiple conditions, we write case If location is L1, then the new value of location will be L2. Here is the condition. Here is what follows from it. The L2 is going to be assigned into location. If the location was L2, on the other hand, L1 is going to get assigned into location. And so basically we have two states where location is L1 and when the location is L2, and we keep jumping from one state to another, like this. To load this model into new SMV, we are going to save it to a file intro.smv. Here is the model. Now we are going to launch new SMV with an option int for interactive. And then we have to load and build this model. To do that, we have to execute the following commands. First, read model with an option E and provide a file name. Then we do flatten hierarchy and encode variables and build model. Then we have to pick an initial state. To do that, I'm going to type pick state with the key -i to do it interactively. We only have one variable and we have assigned its initial value. Because of this, there is only one possible init state in this model. If we had more variables and didn't assign them any initial value, then they would be able to take any value. Hence, there would be a multitude of possible initial values, initial states. This would model an input to the machine. NewSMV would propose us to pick exact values for those variables. Alright, so there's only one available state. I will just press enter and proceed. And the chosen state is 0. Now I want to simulate the execution of the system. And to do that, I will type simulate. This is the first feature of NewSMV. It's simulation. I'll try to use it like this. -i AK4. And it is going to jump me interactively from one state to another. K4 means do 4 steps. And so I've just done 4 steps between the states where location is L1 and location is L2. The key A in conjunction with key I gives me an opportunity to see the values of all variables. All right, this system just keeps switching between 2 states. We have seen that already. If there were cases of non-determinism somewhere where multiple transitions were possible, then the interactive simulation would allow us to pick a transition. Now, recall a simple C program that we have studied some slides ago, with 2 variables, one of which is Boolean variable, so either true or false, and another one is a 1-byte integer variable, so it takes values in range from 0 to 255. Right, this program can be easily modeled in NewSMV. And here is its literal description. Literal translation, like 1-to-1. Let's try to basically load it up, fire up on USMV and do exactly the same thing. Simulate it. So this this program is stored in a file called intro-1. I'll start by reading model from it. Then, as usual, flatten hierarchy in code variables. Build model, pick state, and then I can simulate. Let's pick, for example, 6 first states of this program and see where it gets us. So until the state 1.5, there was some action, but then it seems that we have entered a loop, and from this state onwards we keep getting back to the same state without any progress. Is this what really should happen? Yes, actually, this is totally correct. From what we have seen when we were observing this program and studying it as a C program, we understand that this is exactly what happened, and USMV confirms that. And now that we know a little bit what is going on in this program, let's try to go to the most delicious part of the conversation, which is automatically checking the properties of this program. All right, let's start by something that is trivially true. I think without question we see that because x in the last state x is equal to 2, it will never ever get to 3 or 4 or 5 or anything like that. So we can see that in any state, in all states, x should be less than 3, let's say. Let's check this formula. In order to do that, we are using check LTL spec with a key P, and then in the quotes we can provide the formula. So for all states, x is less than 3. Is this correct? Yes, it is correct. It is correct for all reachable states. Now let's change it to x is less than 2. Will this hold? Well, obviously no, because already here we get to the point where x is equal to. This can't be true. And this is what LTL counterexample provides us. It provides us a trace with 1, 2, 3, 4, 5 states, and in this state it's no longer true. This formula is violated. This is what we are searching for. We are searching for counterexamples to our formula, to our properties that we want to check. All right, no surprises here. Now let's try something different, something less trivial. Is it true that at some point of execution there is going to be a trace where x is going to be greater than 3? No, this is not going to be true, because from this point onward we enter a loop and we never exit it. And in this trace, in all previous parts of it, in all previous states, this formula, x is greater than 3, was false. This property didn't hold. So it didn't hold in the first states, and then we enter the loop, and we never are going to escape it. So here is another counterexample. Let's try one more example. Let's check two mutually exclusive conditions. So the first one will be always if x is equal to 2, then b should be true. Well, there is only one state where x is equal to 2. Then we enter a loop and we never escape it. And it's obvious that because b is true here, then it's going to be always like that. The formula will hold. Now, if we change true to false, it should provide us with a counterexample. That's how it does. But is it true that, let's say, if b is true, then x is equal to 1. No, it's not true either. And what about this? X is equal to 0, or x is equal to 2? No, it's not true either. So if b is true, x can be 1, x can be 0, x can be 2. And yeah, this is just not true. All right, so what about verification? We have provided an example of how it works, but why do we even care about this? Why do we need that? Is there a lot of different domains where this verification thing is of any importance? Well, there are actually domains where verification shines, because other ways of increasing our trust in software either fail or are not effective. And the first thing is the verification of hardware. And the problem here is that once you get a tiny error in hardware, you can't really fix it. You have to throw the faulty hardware away and create new one. There was a story when a large shipment of Intel processors was recalled, and Intel had to basically replace lots of those processors who were already sold, because there was a fault that was not correctable by the firmware update in any way. It was related to floating point arithmetic. The second thing is protocols. Protocols and everything that is distributed actually is very difficult to test precisely because of the non-determinism. So whenever we have to analyze network exchange protocols or analyze some properties of distributed systems, like guarantee the cache coherence, this is where verification and model checking may be of a great use. Anything related to distributed algorithms in general, like clouds, DHT algorithms that you are using in a hidden way when you are downloading something from torrents, the distributed databases and the consensus algorithms, it all has to be verified. And then there is a category of systems where failure is just so expensive that it's not really an option. You don't really want a rocket to be just tested and not verified, because an error in the firmware, in the software of rocket, leads to the rocket falling in the wrong place or just exploding mid-air. Totally not something you want to have. You don't want the power plant to shut down because of some minor bug, so you have to verify the software. when it comes to life support system, a failure in software is a death of a person. A failure in some robot that assists surgeons may be a death of the person. And a failure in a space ship or some kind of space machine sent to Mars, for example, means that a new machine will have to be sent there, because you can't replace it just like that. You have to send a rocket, and in some months it will reach Mars, and it will deliver a new Curiosity or some other Mars rover. So here are the most important use cases for the verification. If you don't know about verification and you are not familiar with that, you are never going to be able to solve any of those problems. You will try to solve them, but then in the end the system that you are going to build is going to be not robust, and it will produce huge losses for your employees. If you are interested in model checking, here are some keywords for your research. If you want, feel free to check them out, do a little research yourself. Okay, to conclude today's part, we have studied examples of deterministic and non-deterministic finite state machines and transition systems. We have learned that if the system is easy to describe as a finite state machine, then we should absolutely do it. And then we can encode this finite state machine on a target language with very little effort. We have observed the differences between deterministic and non-deterministic behavior and provided some examples from more conventional programming languages. Finally, we have been exposed to the concepts of undefined behavior and totality. We have learned how to make any finite state machine total. And finally, we have glimpsed at how limiting the expressive power of a model of computation can bring us great benefits. Designing a program as a transition system and verifying its properties formally allows us to construct robust systems with guaranteed properties. And in the next part, we will study more models of computation, including Intel 64, which is also called AMD 64 computers. And we will start programming in assembly. And we will see how to implement finite state machines in assembly and how it radically decreases the difficulty of building systems even in a language so verbose and so hard to use as assembly is. Hope you enjoyed our time together today, and see you next time.